we're coming to our last 20-minute talk, and as I said, we've got Jeremy Bennett from Member Cosm before lunch. But our next speaker is Marcela Zachariasova from CODASIP, where she's the verification group leader. Marcela is currently a verification group leader at CODASIP and assistant professor at Brno University of Technology in the Czech Republic. Her team is focused on verification of application-specific processes developed by CODASIP, while 2 of these processes are currently based on the popular RISC-V, RISC-V specification from Berkeley. And her title of her talk is RISC-V Process Variants, Challenges and Strategies for Functional Verification.
Thank you, Mike. Good afternoon, ladies and gentlemen. This talk will be about challenges in RISC-V processors verification, and mainly about how we can tackle such challenges by suitable verification strategies. I believe many of you already heard of RISC-V. It is free to use, modern and open instruction set architecture ISA from the University of California, Berkeley. It was originally designed to support research and education, but now it is a standard, new standard for industry implementations under the RISC-V Foundation, and CODASIP is one of the RISC-V Foundation members. A huge advantage of RISC-V is that it is not patented, and it is allowing an ecosystem of processor suppliers, hardware developers, software companies, verification companies to grow. Many small-sized companies, medium-sized companies are contributing, so a potential buyer doesn't have to be worried about being dependent only on one source. As for CODASIP, we do not develop only RISC-V processors. RISC-V is actually reflected only in our Codex Berkelium set of processors. But in general, CODASIP develops IP processors, IPs for IoT domain. So for example, we have Codex Helium, which is targeted to low power, Codex Cobalt, which is targeted to high performance, or Codex Titanium, which is a powerful VLIW core. Nevertheless, the main topic of this presentation are challenges in RISC-V verification. The main obstacle is that despite RISC-V has a very nice standard for ISA and partially also for microarchitecture, you can easily derive many specific hardware implementations from this standard. This diversity originates in instruction set extensions which are optional. So the only mandatory part is the integer instruction set, and then you have many optional extensions like multiplication and division, atomic instructions, floating points, even with double precision, quad precision. You can have compressed instructions, or you can use different sizes of registers, 32, 64 bits. So as a result, we do not verify only one processor, but many of its variants with disabled, enabled extensions. So by the way, there are at least 100 viable hardware architectures that can be created. Together with TVS, with Mike actually, we have identified 2 factors for minimizing the cost and the risk in verification of RISC-V. The first one is automated generation of the processor, meaning the RTL, its SDK, I mean software tools, and UVM-based verification environment for every variant of RISC-V. And by the way, you will see that by CODASIP tools we can do this in the order of minutes. The second factor is a high reuse of existing parts of the verification environments which were added manually by verification engineers in order to increase the level of verification, to increase detail in verification. And I will talk about these 2 factors in more detail on the following slides, and I will start with verification automation. In addition to processor IPs, CodaSIP is also providing a processor development environment called CodaSIP Studio. And when we develop a processor, we firstly describe it at a high level, a high abstraction level, in architecture description language called CODL. Here, we are at the beginning, we are creating two models. The first one is called instruction accurate model, which is describing ISA of the processor. And then we are creating cycle accurate model, which is describing the microarchitecture. So, for example, pipeline, the coding logic, fetch logic, timing, and so on. You can create these two models from scratch in case you are creating completely new processor. Or, of course, you can use our standard IPs and, for example, to modify them by new instructions or some optimizations. What is important is that from these two models, you can automatically generate software tools, SDK, needed by designers like compiler, assembler, linker, instruction accurate and cycle accurate simulators, profilers, debuggers, and even the circuit representation of the processor at the register transfer level in VHDL, Verilog, System C, System Verilog. So it is well known that generation of RTL of the processor and SDK can save design time. However, it is not clear how it can shorten verification. And together with TVS and based on our experience with developing of processors, we defined a number of ways in which it can. Fewer bugs. Of course, once the tool generating RTL is debugged, then certain types of bugs no longer occur. Verification environment generation. We are able to generate RTL SDK from the high-level models. And from these high-level models, we can extract all the necessary information which is actually needed also for generating UVM verification environment. And please note that this goes way beyond simple templates. We are generating complete verification environments with reference models, with coverage points, with assertions. Reference model updates. As well as new RTL, which serves in verification and design under test, we can generate reference models from the high-level instruction accurate model in C, C++. We can do this because architecture description language is a significantly higher level of abstraction than RTL is. So we can consider it really as a reference, and it is reference for us. Then when you have a ISA, when you have microarchitecture described, there is no problem for us to generate also tests for checking these features, their features. So we have integrated a tool for producing random assembler programs, which are then evaluated in UVM. Here you can see the automation flow for verification. So as you can see, we are able to generate UVM verification environment from the high-level models. We have their reference models generated from the instruction accurate model. We have RTL generated from the cycle accurate model. And also we can generate tests, meaning programs, assembler programs, which are evaluated in UVM. Okay, here are examples how generating RTL can be beneficial in verification. So we can avoid fat finger errors, typos. We can avoid some logical errors, for example, in interrupts handling, the coding logic, bit width conversions, pipeline control, ALU operations, write back, fetch logic, and so on. Because actually these logics are generated based on the same algorithms, so for all processors they are quite similar. Then connectivity errors. You definitely know when you have a lot of components, instances in the top level, and you need to connect them together, it is not a trivial task. We can argue about readability of the generated code, of course, but we have links to the high-level model there. So, and it makes life easier because the goal is that if you want to change it, you do not change the RTL, but you change the model and you reuse the generated flow, the automation flow to get RTL again. And RTL generator has been made robust by the years of use, so I believe it is safe to use it. Here is just a recapitulation of the verification automation flow. So these two blocks, these high-level models, are the only part that is written manually by designers, and the rest of the verification flow is automated. Here you can see a description how our random generator engine works. So you can see that all you need is the high-level instruction accurate model, configuration in CodaSIP Studio, meaning how many programs with how many lines you want to generate, and user constraints which are optional part and can be used to define the correct flow of the program, or you can increase some probabilities of instructions. Then these random programs are evaluated in UVM, and we are checking coverage, of course, and if high-level coverage is not reached, then it is a feedback for us, for verification engineers, that we should write some directed tests. Okay, to summarize this section, automation in generating RTL, UVM, and reference models and tests can rapidly improve productivity in the development of RISC-V cores, and in CodaSIP we can do this automation in the order of minutes. Therefore, we do not spend valuable time on code writing, but rather on real debugging and exploring corner cases. The second part is devoted to strategies favoring reuse. And when we are considering RISC-V cores, then it is beneficial to actually start verifying the most complex variant you currently have, and use the automation flow to get all the tools and resources, and also manual additions to the generated version to check the processor properly. Here, when you are verifying a simpler version, then again you can utilize the automation flow, but you can also reuse existing parts of the verification environment for the more complex version. And what can you reuse is listed here, so you can reuse test constraints for the generator, directed tests, assertions, coverage points. Let's demonstrate this principle on a series of pictures. So let's suppose that we have a complex model, RISC-V model called Berkelium-5 from CodaSIP. It is 64-bit with integer instructions, multiplication, floating point compression. Here you can see the automated flow. So we generate RTL, reference model, UVM verification, and ISA test, random assembler programs. Then when you are creating this verification environment for the first time, of course you can find some mismatches between the reference model and the RTL. These mismatches must be debugged, and if we find some bugs, the goal is to modify the high-level model and regenerate all the tools and RTL. Then when results are okay of the comparison, but we are targeting coverage. If it is not 100% or close, then it is a feedback for us that we need to add some parts manually. So for example, directed tests, assertions, or coverage points. Then when also coverage is 100% and results are okay, we can consider verification as finished. When a customer wants a sub-model of the more complex variant, what we do, you can see that the submodel is 64 bits with integer and multiplication only. We again regenerate all the tools and RTL, but we do not expect to find any mismatches because we already debugged all of this, and we are targeting coverage only. So what is a huge advantage? You can reuse, copy, directed test, assertion, coverage points from the full verification environment for the full design. And then again, if results are okay, coverage is okay, we can consider verification as finished. Here you can see an example when customer wants an extended model. So you can see the complex variant plus some kind of extension. again, we generate all the tools and resources. We can discover some mismatches, but only we can suppose that only those which are connected to extensions. Then we are targeting coverage again. We can again highly reuse existing parts, and we can add some new parts connected to the extension. So you can see that really the automation and reuse can really save design time and increase productivity rapidly. Okay, so to summarize this section, in addition to automation, when verifying a simpler variant of most of the it wants to okay. Or when adding a user extension, we can highly reuse existing manually written parts of the verification environment. And that's it for me. Thank you for your attention.
Thank you. Thank you very much. Are there any questions? Marcela? Yeah. I'll start over there and I'll come back. I'm going to take the most efficient route. Even though I know it's MP complete, but I can do something surely.
Hi, Paul Tiernan from Imagination Technologies. If you're using the same engine to generate your RTL and your reference model, how do you decouple them such that they're different? And
okay. Actually, when you look at the instruction accurate model, which is used for generating RTL, and when you look to the cycle accurate model, which is used to generating RTL, they are really different because the instruction accurate model describes ISA, so instructions and how they should behave. And cycle accurate model is describing the microarchitecture, so details about the microarchitecture like pipelining, timing, and so on. So it is adding really a lot of information to the instruction accurate one. And we consider the instruction accurate model as a reference because really there we can find the reference functionality.
Ashish Sarbari, OneSpin Solutions. So when you're actually running your test bench, are you verifying the whole CPU end-to-end, or are you actually having to do any block level verification? Because I'm wondering where you get your constraints from if you were going down the route of doing load store unit on its own and so on.
Okay, we are of course our processors are constructed from blocks, and internally we are verifying also these blocks, and then we are building the processor. But what I demonstrated here is the processor, the top level of the processor. So yes, internally we also use separate verification flow for sub-blocks, and also at the top level similar approach.
How do you get your constraints?
You mean constraints for the generator?
Yeah, for smaller blocks when you're verifying them.
Okay, when we are verifying the sub-blocks, then there we use constraint random approach, and it is defined by the block itself, so we do these constraints manually. What I presented here are constraints for the program generator.
Hi, this is Nayan from Cirrus Logic. My question is almost same as the first question. So you have a same source to generate RTL and verification test bench. So if there is a bug in your architecture description, you will have bug in RTL and bug in, you won't be able to catch that bug in RTL because what you're expecting from verification is same as bug in RTL.
Okay, so maybe I repeat my answer again, that the instruction accurate model and the cycle accurate model, they are written in the same language, you are right. But these two parts are different, really. So when you are describing instructions,
sorry to interrupt you, but you said they both are automatically generated from architecture description, right?
No. No.
Okay, so they written manually.
Well, I'm sorry?
So those both models are written manually?
Yes, they are.
Okay, thank you.
Okay, thank you very much. Thank you. Thanks much.